a very interesting result of the symmetry of physical property is that if any physical property is represented by second rank tensors, they are centrosymmetric, whether the crystal is centrosymmetric or not. We have seen that out of 32 point groups of a crystal, only 11 are centrosymmetric. Centrosymmetric point groups, and the remaining 21 are non-centrosymmetric. They lack center of symmetry. But if a physical property is represented by a second rank tensor, for example, electrical conductivity, it does not matter whether the crystal has the center of symmetry or no. The property will always have the center of symmetry. So, second rank tensor property always has a center of inversion. Whether the crystal possesses that center or not. So, this is an additional symmetry. You can see if the crystal has center of inversion, then property should also have center of inversion, that is assured by Neumann's principle. But if crystal is not having center of symmetry, then still property is having a center of inversion. So, that falls into that category, that property must include the center of must include the crystal symmetry, but may have more symmetry. So, for 21 non-centrosymmetric crystals, the property second rank tensor property having a center of inversion is an additional symmetry. So, why is this the case? Let us have a look at it. So, first, as we said, that property having a center of inversion means if we have the axes. So, let us say that the property was measured in some axis system x 1, x 2 and x 3, and let us introduce another axis system which is related to the first axis by inversion. So, I invert all axes in the center. So, the red and the blue axes are related to each other by a center of inversion in the origin. The property having center of inversion means that if I represent the property in any of these two axis system, the property will remain the same, it will not change. That means, the tensor, the second rank tensor will remain the same during this coordinate transformation. So, let us see what is the A matrix for this transformation, the coordinate transformation matrix. So, we write x 1, x 2, x 3 on top, the old on the top, x 1, x 2 prime, x 1 prime, x 2 prime, x 3 prime on the right, and we simply note all the direction cosines for these pair of directions, the cosines of angle between these pair of directions. So, x 1 prime, if we choose x 1 prime makes 180 degree with x 1, cos 180 degree is minus 1. So, I write minus 1 there. X 1 prime is perpendicular to x 2, cos 90 0, x 1 prime perpendicular to x 3 cos 90 0. So, that gives me the first row. Now, focusing on x 2 prime, similarly we see that it is 0 minus 1 0 and x 3 prime gives 0 0 minus 1. So, this is the A matrix relating these two coordinate axes, and if we say that the property is centrosymmetric, then the property should not change under this coordinate transformation. So, let us look at let us think of a general tensor T, which is represented by its 9 components. So, if we now transform this tensor by the coordinate transformation, I should get the same tensor. So, how is that true? So, we have seen that the coordinate transformation, the transform tensor T prime, it is written as A T A inverse. We have also noted that A in the orthogonal transformations, A is always A inverse is nothing but A transpose. So, we can write A transpose, but note the particular values of A. In this case, A is nothing but negative of an identity matrix. So, if you note that, so all you have to do is instead of A, you have to write minus I T and minus I transpose, which is minus I T and another minus I. So, you can see that this becomes plus I T I or plus T, because identity matrix does not change the matrix to which it is being multiplied. So, T prime turns out to be exactly the same as T under this coordinate transformation. And what was the coordinate transformation? Coordinate transformation was relating a center of inversion. So, that means the property has this center of inversion, and we did not worry in this derivation whether the crystal was having this center of inversion or not. So, any second rank tensor property will always be centrosymmetric. Thank you.